Hello, students. Hope you all doing well. Can you hear me? Hello.
Yes, sir.
Yeah.
Yes, sir.
So yes. In today's class, we are going to discuss experiment two. So just like previous class, some of our TAs today we have Vishal and Shekhar. So they will be presenting the second experiment, the stuff related to second experiment, and also the V labs. They will show uh, a bit of demo of V labs that you have corresponding V labs. I hope you are able to do your first experiment, and today is the deadline. So we will postpone your deadline a couple of days because I think some of the TAs did not. We did not have that chat box, so we'll kind of postpone a couple of. We'll give you a couple of days more for the experiment one. It's the first experiment, but henceforth we are not going to do any postponements. Okay. So experiment one, you had to uh, go through that quiz and submit that. In experiment two, actually, it will be full-fledged experiment. So you need to do the experiments that are available in V Labs and then submit all the details that are actually explained or given in that particular document that I shared last class, okay, that guidelines PDF, right, that I shared in the last class. One thing is that Professor Bhattacharya actually has already shared a video with you, maybe a couple of hours ago he shared, and that contains actually a hands-on. It shows that what you would have done, okay, if you are there in this semester, you are there here physically, and what you would have done on the kits that are available in our labs. So it is shown there, but it's kind of different from what you are going to do in VLab now. But please go through that video because you will be having a quiz right at the end, and we might be asking some questions from those videos as well. Okay, such videos will be shared in few of the experiments, and you should go through them. Okay, so I think I will hand over to the TAs. They can start. Okay, so experiment two, Vishal will take over.
Hello.
Experiment.
Hello.
Yeah,
Yeah, I'm
Vishal.
audible.
Yeah.
Okay. Yeah. So, is my screen visible, sir?
I can. Yeah, it's there now. Yeah.
Yeah, it's visible, right? So, I guess presentation is visible.
Yes, it is.
Okay. So, hello all. This is your experiment 2, and your experiment 2 is basically divided into two parts. First one is Ohm's law, and the second one is RC circuits. So that is Ohm's. This one is Ohm's law, experiment 2, part 1. So you all know what Ohm's law is, and the objective of this experiment is to define what is Ohm's law, define Ohm's law for resistance in series, Ohm's law for resistance in series and parallel, and how Ohm's law behaves in non-ohmic devices, and finally we will measure and confirm Ohm's law in VLabs. All right. So this is the Ohm's law. You all know about this. That is current across a conductor is directly proportional to voltage across these 2 points where we are measuring that current. Right. So I is directly proportional to V, and that's how we can say V is equal to IR. And this is a basic circuit. This is Vs, a voltage source that we have applied across a resistor R1, and we are measuring the voltage across this voltmeter, which is across this resistance, and we are measuring current through this resistor. All right. So that's why, and you all know that we connect voltmeter in parallel to resistor and emitter in series, because in series we need to calculate the current in series, because emitter has zero voltage drop, and ideally emitter has zero voltage drop. So we are placing the emitter in series, and we are placing the voltmeter in parallel because voltmeter has zero current. So zero current will be flowing through here, so all the current will be flowing through resistor, and all the voltage drop across the resistor will be calculated through this voltmeter, and all the current will be through emitter. All right. So VR is equal to Vs. Ideally this VR will be calculated through this voltmeter, and VR is equal to Vs, and the current through emitter I is equal to VR by R, the resistance, the voltage across resistance divided by resistance, and that is VR is equal to Vs, so Vs by R. Right. So this is resistor in series. When resistors are connected end to end, they are called resistor in series. the current flowing through all the resistors will be same, and the voltage will be dropped across each of the resistors. So V1, V2, and V3 is the voltage drop across R1, R2, and R3 respectively. So V is equal to the voltage drop across summation of voltage drop across each resistor. So V1, V2, V3, and as the current is same, so IR1, IR2 plus IR3. And that's how we can say, like, if we take I in common, so R1 plus R2 plus R3 will be equivalent resistance in this circuit. And then resistance in parallel, when each both end are connected together of resistor, they are called resistance in parallel. In this case, voltage will be same across each resistance, but the current will be divided. So the current I is flowing through here, and the current will be divided like I1, I2, and I3. And the voltage across is, this is I1 R1, I2 R2, and I3 RT. But these three will be equal in this case. But the current is I is equal to I1 plus I2 plus I3. So I is equal to I1 plus I2 plus I3, and I is V, this voltage, as the voltage is same across all these three. So V divided by R equivalent of this resistance combination. So V by R equivalent is equal to V by R1 plus V by R2 plus V by R3. So current is divided and voltage remains same. And about non-ohmic devices, the statement is pretty straightforward. Like any device that does not follow Ohm's law is non-ohmic device. And the example are diode, capacitor, inductor. Because the current and voltage relation is not linear, that's why they are non-ohmic device. All right. So we will see in the experiment how they behave. So I will like first I will demonstrate the VLab experiment, then I will go to the part 2 of this experiment. Just a second. Right. So in this list of experiment, you can see the fourth number experiment that is Ohm's law. This is your first experiment, and then 13th and 14th is your RC circuits. This is part 1. This is RC circuit part frequency response and RC circuit differentiator integrator. So this one is Ohm's law. You will see the theory here. I have explained pretty much everything here. All right. So procedure, I will explain the procedure in the simulation part. So you can read it. And this is simulation. So first one, we will verify Ohm's law. So let us take a simple straightforward voltage, like say I set it to 10 volts, and I take resistance like like 50. Let us take 50. All right. So you can see the current is like 0.196. If I set it to 50, you can see it is 0.20. That is like 10 by 50 is 0.20. All right. So now V is equal to IR. That is confirmed because like the multiplication. And let us fix the resistance and vary the voltage. That's what you gotta do in the experiment. Like set to voltage, change the voltage to 5, add to table, just increase the voltage and keep the resistance constant. Like you will see this, you are seeing this table, that is due to resistance is equal to 50 kilo ohm, and this is the voltage and the current relation. And you can confirm in each that if you divide to any voltage value by divided by this resistance value, you will get this current value. And if you plot this, you will get a straight line. This straight line defines the Ohm's law, that V is equal to IR, and that V is directly proportional to I. And that you can see in the graph. And the slope of this line is nothing but our resistance, that is 50 kilo ohms. All right. That is the first part of your experiment. And you can see the draw circuit part in every like Ohm's law draw circuit, Ohm's law in the resistance for series draw circuit, and Ohm's law in parallel. I'll explain this one, and then you can do other. So in this, what you gotta do is like you just have to connect these. And voltmeter, I've already told you that you gotta put it across parallel in resistance, and emitter will be connected through this resistance and through this. And don't forget to connect the ground. So just now it's the same circuit that we did before, and you just have to like put any value and you will confirm this, like you can see here. All right. And just to check the connection, you can just check this. You will see it will pop up like right connection and set resistance and input DC voltage. Right. So that's it. And now for Ohm's law for resistance in series, it's the same thing. Like you just have to change the voltage and set the resistance values. Let us like, because it is in series, let us put this in 30s. This is 15. All right. So 35. So 35 plus 15 is 50, and 10 by 50 is 0.200. Hence Ohm's law in series is this only. Like just add these two, it will be 50, and just apply the Ohm's law straightforward. Then for the parallel circuit, that is Ohm's law in parallel, you can see here it is in ohms and this is in kilo ohms. So just I'm taking a simple value. Sorry. like 1 kilo ohm, and here also I'm taking 1 kilo ohm, like 1000 ohms is 1 kilo ohm only. So 1 kilo ohm and 1 kilo ohm in parallel is nothing but 500 ohms. Okay, so resistance is divided by 2 if they are same value in parallel. So if I take a voltage 20 and the, as you know that I have set the resistance to 500 ohms, so 20 divided by 500 will be 40 milliamperes. This is in milliamperes. You can see this in table. This is in milliampere. All right. So 20 divided by 500 is 40 milliamperes. So you gotta plot this, add to table, and just change the value of this, and just add to the table, and you will plot this graph. You gotta plot the graph in everything. So, and the last one is verifying non-ohmic devices. So in this, you just have to change the voltage to 5 volts, and you just change the resistance value to anywhere. Someone is saying something.
Actually, I think there is some delay. Some sometimes whatever you're saying, the thing is appearing a bit late, so you can be a bit slower. So
Oh,
because of the
okay.
internet connection, maybe, or something. Yeah. So you're saying that it is happening after some time.
Okay, sir.
Uh,
So we will change this resistance value, and as you can see, this resistance value R, and you just add it to table and just increase the resistance value. So if you see these values of voltage across this uh, diode, this is diode, and the voltmeter is placed across this diode. If you plot this voltage versus current graph, you can see this is a little bit curvy. This is not a straight line. So that's how that's how current versus voltage relationship in non-ohmic devices. As it is not a straight line, so diode is a non-ohmic device. So this is the experiment 2 part 1. Like these 7 things are the experiment 2 part 1. Any doubt till now? Anyone?
Yeah, one thing is there. Whatever Vishal is explaining in all the V labs, you always, I mean, you have something like instruction top left. Okay, if you click that, whatever he's saying, actually it is listed there. So what connections you have to make in the draw circuit, and in the other ones, how to like plot, and what values you need to take, and how many values you need to take. All those things are actually written. Okay, if you click on the top left instruction, there is something called instruction written there. So if you just click on that, yes.
Okay.
If you have any question, ask him.
Any doubt in the part 1? Okay. So let us continue with the experiment 2 part 2. This is RC circuit, and this is also divided into 2 parts. RC circuit is first is RC filters, and second one is RC integrator and differentiator. So I'll start with RC filters. So this experiment is RC filter, and in this we will see how to use RC circuit as filters. And your VLab experiment contain RC circuit as a low pass filter and RC circuit as a high pass filter. Right. So RC, we basically plot the frequency response of the filter, and we see how that is like how the circuit is responding to different frequency ranges. Right. So filter is something that allows a specific range of frequencies and attenuates signals of other frequencies. It like it is divided into 4 parts. Like there are many filters, but commonly there are 4 filters: low pass filter, high pass filter, band pass, and band stop. So low pass filter is something that will allow low frequency. High pass filter is that will allow high frequency. Band pass is something that will allow only a band of frequency, and band stop is that something that will only stop some band of frequency and will allow every other frequency. And there is a term called cutoff frequency in the frequency we talk in when we talk in frequency domain, or when we talk about filters. That is cutoff frequency. And cutoff frequency is that frequency at which the magnitude response is a part of frequency response. Magnitude response is 3 dB lower than the value at 0 hertz, or it can be higher than the value at 0 hertz. Because when we talk about high pass filter, we will see that what is the value, but where 3 dB value is higher than the 0 hertz frequency. And it is also called the minus 3 dB frequency, because at this point the frequency of the filter is approximately minus 3 dB than the 0 hertz frequency, whatever the amplitude is at 0 hertz. All right. So frequency response, And frequency response is the curve between amplitude and phase. Amplitude curve is different and phase curve is different, and we plot both the curves with respect to frequency. We vary the frequency and we see how the amplitude and the phase of the circuit is changing with respect to frequency. And high ideal, we have like as our elements are not ideal, we have like in capacitor we have some kind of resistance also, and some hidden reactance and resistance are there. So ideally the curve should have a sharp change, like, and I will show you in the picture. But ideally ideal curve frequency response should have a sharp change, but practically it is something different. And the frequency response is divided into two part: amplitude plot and phase plot. Amplitude plot is something that is plotted in dB scale. DB scale is a logarithmic scale in which we take the amplitude in logarithm, and the phase plot is plotted in degrees. All right, but the frequency will be in hertz. So this is a low pass filter, and in the left side you can see is a ideal case. In this, if you see here FC, this FC is the cutoff frequency. This FC here you can see this is the cutoff frequency. At this frequency there is a sharp edge, like this is the passband, and after that it will stop any frequency. All right, so this is an ideal case. But in practically what happens is, at the cutoff frequency, what we measure is at cutoff frequency we see where the 3 dB point is lying. Like at here we assume that there is 0 dB amplitude, so 0 dB minus 3 dB, this is minus 3 dB point, and we will see where this point is corresponding in frequency. So that point will be taken as cutoff frequency, and we will say that till the starting and till the cutoff frequency, that is our bandwidth of the filter, and this is our pass band, and after cutoff frequency that is our stop band. All right, and this is there is something called order of the filter. We will not dig into that, and due to that, it just for your sake, it is first order filter, so we will be taking here minus 20 dB per decade. In the first order filter it is minus 20 dB. Right, and this is a phase response of our low pass filter. It starts off with 0 degree. At cutoff frequency it goes till minus 45 degrees, and it goes till minus 90 degrees. All right, and this is our high pass filter. At high pass filter in at cutoff frequency of high pass filter, there is a sharp turn. It will allow frequency after FC, and it will not allow before this. So this is stop band and this is pass band of a high pass filter. And as in practical case, at cutoff frequency the frequency is this is minus 3 dB. All right, this is minus 3 dB point. So at this minus 3 dB you can see here, so minus 3 dB, this is cutoff frequency, and after this will be a pass band and this will be stop band. All right, and the phase response also it will start with plus 90 degree. At FC it will be plus 45 degrees, and it will go till 0 degrees. This is the phase response of the high pass filter, and this is the amplitude response of the high pass filter. Right, and this is a circuit of low pass filter. Circuit basically looks same in because this is a common RC circuit. It just see where we are taking the voltage. In the low pass filter we are taking the voltage across this capacitor. So V out here, and the reactance, this XC is reactance of capacitor, and we when we apply like a voltage divider, V out is equal to V in. The if we calculate this V out, it will be like the resistance across this divided by resistance of the circuit, so and multiplied by the input voltage. So V in into XC divided by resistance of the circuit, and this is nothing but root R1 plus R1 square plus XC square, and XC is the reactance of this capacitance. And the phase is minus tan inverse of 2 pi FRC. F is the frequency at which we are operating. This is an AC input. So frequency at which we are applying resistance of this R on this capacitance. So this is phase minus tan inverse of 2 pi FRC. All right. And the cutoff frequency is given by FC is equal to 1 by 2 pi RC. Cutoff frequency I have already told that wherever that there is a minus 3 dB point. And XC will be 1 by 2 pi FC. That is how reactance of capacitance is given. FC is cutoff and XC is reactance. And this is how RC high pass filter look like. And I have already told you the circuit eventually is same, but it differs where we are taking the voltage. So in this, we are measuring the voltage across the resistance. In this one, we took the voltage across capacitor. So as in this, like this is nothing but r. We will take this across r upon my r square plus x square. R square root of r square plus x square remains the same. Just the numerator part is different because in that we were taking across the capacitor. That's why xc, and this in this r's. All right, and the phase is given by pi by 2 minus tan inverse of 2 pi frc. And you must have seen the in the graph that the plot starts at 90 degree and goes till 0 degrees. So this will term at infinity eventually that goes to 90 degrees. So this will, the phase will go to 0 degrees. All right, and the cutoff frequency remains the same in both the cases. X is equal to 1 by 2 pi rc and x is equal to 1 by 2 pi fc, that is the reactance, and cutoff frequency will remain the same in both the cases because cutoff frequency's property of the circuit is not a property of the input applied. All right, you can see nowhere it is written the input voltage or output voltage or the frequency. Nothing is there. The cutoff frequency is only dependent upon the circuit component. So that's why 1 by 2 pi rc. So low pass and high pass has same cutoff frequency. And for illustrative purpose, I have taken the value of resistance is equal to 4.7 kilo ohms and capacitance is equal to 47 nanofarads. And when we plug in these two values in this formula, we will get cutoff frequency something 720 hertz. All right, this value I will use in the VLab experiment. So just keep this in mind. I have taken these two values. These are pretty much practical values commonly used. So that's why I have used these two values, and we'll get cutoff frequency equal to 720 hertz. And now I will go to the experiment part, VLab part. So in this 13th one is RC frequency response. Theory I have explained, simulation part, and this RC low pass filter. So I told you that I took RC as R40 for 4.7 kilo ohm and it is in ohms, so 4.7 kilohertz. And the last value in this is 46.91, so I'll taking this only. So let us assume that it is 47 nanofarads only, and just I will set the voltage at 5 volts, and just for the starting frequency, let us take as 50 hertz. Mind you that the cutoff frequency was 720 hertz, and we will add this values corresponding frequency value into the table. I will just change the values and add it to the table. Just one more. All right. So in this, you can see the value is minus 0.02. So you can see that attenuation is very less, like 0.02 dB is very less. And at 149 hertz, it is 0.17. At 438 hertz, it's minus 1.3. And at 3818, it is minus 14. And you can see the minus 3 dB point will lie in somewhere in between these two values, 438 and 3818. All right. And you can see this value is lesser than minus 3 dB. So when we plot this, you will see here two options, frequency response and phase response. First, we will plot frequency response of the, that is basically amplitude response. So you can see that the x-axis is frequency and the y-axis is magnitude. You can see this is 0 dB line, and this started decreasing, going downwards in here. And you can see that minus 5, minus 3 will lie somewhere here, right? So if you go till here, minus 3 point, you will see that this is nothing but 720 hertz. This point here will correspond to 720 hertz only. So at minus 3 dB, 720 hertz frequency will be there. All right. So this is how your that frequency response curve will look like, and the slope is basically nothing but minus 20 dB per decade. All right. And when we plot the phase response, you can see the phase response is going like tan inverse graph. If you have taken many points, then it will perfectly resemble the tan inverse graph. And this point here correspond to minus 45 degrees. And when you go till here, minus 45 degree will lie somewhere across here. And this will again be 720 hertz. All right. That's how the phase response of our low pass filter look like. And that is again the draw circuit part. You can do this on your own. And then our high pass filter, I'll take the same frequency, plug in voltage, and just add the different values to the table. In this, you can see the magnitude is minus 23 dB. That is much more than our previous low pass filter. In this, you can see minus 23 dB is that is signal is very much attenuated. And at 149 hertz also, it is minus 13. But when we cross the 720 hertz mark, 1294, you can see this is within the limit of minus 3 dB, and it will goes down. It will go down it will be lesser than minus 3 dB as long as frequency is greater than 720 hertz. Right. So when we plot this, you can see the plot. Pretty much looks like a high pass filter that I've shown you in the PPT. This slope is 20 dB per decade. Minus 3 dB will lie somewhere along here, and this will be again corresponding to 720 hertz. And this will be the phase response. Again, tan inverse graph, but this time it is starting from 90 degrees and going till 0 degrees. And the 45 degrees point will be somewhere along here, and this will be again 720 hertz only. So that is all from my side. Now I will like to Shekhar sir to continue with RC circuit as integrator and differentiator.
Thank you, sir.
Any doubt till now? Hello?
Taking minus 3 dB for deciding if C is a standard.
Yeah, actually there is a mathematics behind this. Minus 3 dB. Like when you take the actual formula for that is 10 log output upon input. And when you plug in the value 1 by 2 into like if you take the half power point, in electronics we are very much concerned about the half, where the power is getting halved. So when you plugged in the value 1 by 2 in this, you will get to minus 3. The value will be minus 3 dB only. You got my point?
Yes, sir. Thank you, sir.
Sir, I
Yes.
have a doubt on the formula.
Yes.
Sir, in a formula you have written 2 pi FRC.
Yeah.
And just below it you have written F equal to 1 upon 2 pi RC.
Yeah, the F is that frequency input and the FC is the cutoff frequency.
Okay. Okay, sir.
Yeah. The phase response will be dependent upon the input frequency, but the cutoff frequency is not dependent upon the input frequency. It is a property of the circuit.
Okay, sir.
Whoever asked this question, so if you divide by that, what is happening? So arc tan off, it becomes the tan inverse of what? I didn't notice who asked the question. Somebody asked this question, right? So when you're saying FC is 1 by 2 pi RC, and if you substitute that FC in place of F in phase, okay, so it becomes what? Tan inverse of?
F by FC.
Yeah?
F by FC.
It will become tan inverse of 1. That will be 45
tan
degrees.
inverse of 1, yeah.
Yes.
So that's 45 degrees. That's exactly what he was saying, that at cutoff, the phase will be 45. Okay? Or minus 45
Yes.
in that. Yeah. Okay.
Yes.
Yeah, Shekhar sir, you can continue.
I hope most of you, these topics are being covered in your theory classes, because we kind of think that the most of the theory parts of this will be covered in your theory classes.
So good afternoon, everyone. Is my screen visible?
Yes, sir.
Yes, it
Yes,
is.
sir.
Yeah, we can.
So good afternoon, everyone. Now I will be covering the experiment dealing with the simulation of RC integrator and differentiator. I'll be just touching upon the theory, and then we will be moving towards the simulation part. So the integrator is a circuit that converts or integrates a square wave input signal into triangular waveform output. A basic RC integrator circuit is simply a capacitor in series with a resistor and the source that produces an output signal which corresponds to the mathematical process of integration. The output is taken across the capacitor. As you can see, when the input pulse from the source goes high, the source acts as a battery in series with a switch, and the capacitor starts to charge. When the pulse from the source goes low, battery is replaced with a switch that is closed, and the capacitor discharges. Moving on to a RC differentiator. The differentiator circuit converts or differentiates a square wave input signal into high frequency spikes at its output. A basic RC differentiator circuit is simply a resistor in series with a capacitor and the source that produces an output signal which corresponds to the mathematical process of differentiation. The output is taken across the resistor. As you can see here, the capacitor, when the capacitor looks like a short to the rising edge, because initially when the capacitor which is there, it cannot change instantaneously, and hence during the first instance the output follows the input. After the initial edge has passed and the output source becomes constant, the capacitor charges, and hence the output voltage across the resistor starts to decay. The voltage across C, that is the capacitor, is the traditional charging waveform, and the output across the resistor, which is the output which we require, starts to fall exponentially. Next is when the voltage across C at the instance the source turns off does not change, again because at the capacitor cannot change instantaneously, and once the source becomes again constant, the capacitor starts to discharge, and hence after dropping to a negative value the output voltage starts to rise exponentially as the capacitor discharges. Coming to the simulation part, I hope the oscilloscope tutorial has been covered for all of you. In simulation we have four options here. First is the RC integrator experiment, followed by where the integrator experiment wherein you can draw the circuit and do the experiment, followed by the RC differentiator circuit experiment and drawing the RC differentiator circuit. First we will go to the RC integrator circuit experiment. Wherein, as you can see, as sir had already told, there is the instruction set for people, for anyone who has any queries while undertaking the experiment here. In this experiment, we have the circuit on this side of the screen, on the right side of the top screen, and on the left side we have the oscilloscope screen, below which we have controls of the oscilloscope from wherein we can change the frequency and amplitude, and for controls we have for the channel 1 and channel 2 wherein we can change the position of the y-axis by changing the volts per division. Now to undertake the experiment for RC integrator, you can follow the instruction set which is given here. So first we will set the resistance to say 10 kilo ohm and the capacitance to 0.1 ohm. When you switch on the oscilloscope, you will get option of square wave, which will be the input wave and will be available through channel 1 of the oscilloscope. Once you select the input, then you can get the output from oscilloscope, and the output is if you select channel 1 you will get the input square wave, and if you select the channel 2 you will get the output from the oscilloscope. And you can also choose a dual option in which we can get both the inputs and the output waveform together in the oscilloscope. Now if you want, you can change the frequency and amplitude from these controls. For various frequency and amplitude you can vary the data here. Now in the RC integrator, for drawing the circuit also you can draw the circles again. You can follow the instruction set which is given here and repeat the same procedure. like we did in for RC integrator. Coming to the differentiator circuit, similar process is to be followed here, wherein you set the capacitor value and resistor value. Herein you have to notice that the resistor value is in ohms, whereas in the integrator it was in kilo ohms. You see, for the input, whenever there is a rise in the input, we can see the spikes which is being generated at the output. Again, here you can change the value of frequency, amplitude, and the divisions you want in the oscilloscope. The fourth experiment again deals with the RC differentiator circuit, wherein you have to draw the circuit by making the connections as given in the instruction set over here. That will be all from my side. Anything?
Yeah. So
Any questions?
yeah, you have any queries? Yeah, please ask him. Please ask him any queries.
Sir, I had a doubt that how taking voltage across resistor or capacitor behaves as a filter. Means I did not understand that. I understand the mathematical things, but how does it behave as a filter? I do not understand.
Filtering, I think Vishal, you
Hello?
did it, right? So
Yeah.
yeah, Vishal.
Yeah. Hello.
Filtering, I think the question is on filter, RC filter. So
Could you repeat the question?
Sir, I understand the mathematics, but how does taking voltage across a capacitor or resistor make the circuit behave as a filter? Means if how that
Have you
happens, I do
studied
not
the
understand.
theory of capacitor, like how capacitor behaves at different frequencies? Do you know
I
about
have,
reactance of capacitor?
yes, I know about
Yeah.
reactance.
So reactance is like formula of reactance.
1 by
X is equal
omega.
to 1 by omega c. So you know that value is changing with respect to frequency, right?
Yes, sir.
Yeah. Let me just draw it in a paper. Can you see my screen?
Yes, sir.
So here. So see, when you are taking this capacitor and when we are talking about a high pass filter, when the frequency is low, hello.
Yes, sir. You are audible.
So when we are taking this, when if that frequency is low, the capacitance value will be low. Reactance value will be if this F frequency value is low, the reactance value will be what?
Hi.
High. Yeah. So the voltage, so reactance is high, so the voltage drop across this capacitance will also be high.
Yes.
But when we change the frequency to a higher value, the reactance value will drop.
Yes.
When the reactance value will be dropped, the voltage dropped across this capacitor will also be lower than what it was at low frequency, right?
Yes, sir.
You understand that voltage is directly proportional whatever the resistance is there or the reactance is there, right?
Yeah. Yes, sir.
As the reactance is also inversely proportional to the frequency here, when the if you consider a highest frequency, like if you consider an infinity, this capacitor will act as short circuit.
Yes, sir.
When this is a short circuit, the voltage drop across this will be zero, right? The voltage
Yes.
drop across will be zero somewhere here, right? So and when this is open circuit, when the frequency is zero, this will be open circuit.
Yes, sir.
As this is open circuit, no current will flow, so no voltage drop across this resistor. All the voltage will be dropped across this capacitor, and the voltage will be highest at this point. As you eventually increase the frequency, the resistance will start to decrease across the capacitor. So hence the voltage will also start to decrease.
Yes, sir.
Got my point?
Yes.
You can simply like follow this for high pass filter. When the frequency is low, this will act as
High
open.
resistance.
Yeah, when the
Yes.
frequency is low, this will be high resistance, and this will be open circuit. All the voltage drop will be across this. No voltage will be dropped across this, right?
Yes.
So this will be zero output. This will show zero output at zero frequency. When we increase the frequency to infinite, this will be short circuit, right?
Yes.
As this will be short circuit, all the voltage drop across this will be resembled to output voltage across the resistance. So this will be highest at this point for the infinite value, and in between the value will increase, right? Like the frequency, when you increase the frequency, the voltage drop across this will start to decrease from V in to zero. So this will start like go like this.
Okay, sir.
You understand?
Yes. Thank you, sir.
Any more questions? Any more questions for the TS?
Excuse me, sir.
Go ahead.
In the RC the peaks are not at the places where the square wave is there. Shouldn't they merge with the edges of the square?
Shekhar?
Professor Sen, may I address this question?
Yes, you can.
Yeah.
Of course, why not?
So actually the problem is we have mentioned this in the first class actually. So there might be the cases where the simulation results are not whatever you are expecting, because VLab is a simulation platform, right? So if you are not getting at a particular frequency, you will see that in certain frequencies this might happen because it's not actually a real circuit, right? So in most of the cases you should get the ideal result, but there might be cases where you are not getting it. So the thing is that you just report it in your report that you are submitting, right? So you just make it as an observation and submit it, because the TAs will verify whether if there is any glitch in the simulation platform. You will see that in certain cases there can be incidents where it's not matching the theoretical results. So you just have to report that what is the expected value and what you are getting from the VLab. So apparently, what is your name, by the way?
Venkat, sir.
Venkata, right? Right. So apparently, whatever he's saying is actually true. In the differentiator, it might happen that the peaks for the output is not matching the input signal. Even if you do this exceptional shift and everything.
No, sir. I was asking that the
Is it clear?
output is always same, but even though we change the input channel one through the channel one, it is giving the same output.
Should not. Let me just check.
Yeah, so this could be a potential, I mean, glitch in VLab. Is he right when what he's saying? That's why I asked Shekhar, because he was
That's what I'm saying. That might be a glitch actually. I mean, that might very much happen because there might be some glitch in the VLab itself.
So one thing which I have observed, not in this experiment, but in other experiment when I was doing it, what I observed is that it sometimes it does not update according to you are changing the input, and the output remains same. This I have observed actually. I think this was the question, right? That very similar question you have asked. So I think if there is any issue like that, say one input you have given and you have got an output. Now, if you are changing the output and you expect the you're changing the input and you expect the output to change and it's not happening, then please refresh the entire thing and start from scratch and give the second input again freshly. Okay, so I have tried that and sometimes it works.
Nice point, Professor Sen. Actually, that happens. You have to sometimes refresh the entire page before starting the experiment. True.
So if, for example, the differentiator and the integrator, you have to take a few examples. Okay, you can vary the frequencies and you have to give few examples, and then you have to show in your report. So after first example, you can refresh the entire thing and then take the second example. Okay, and then you take the output. That would be, I think, that if that does not work, then nothing will work. Actually, it should work. I think VLab, we saw that this VLab for this experiment was okay, right? There could be some refresh issue that you have to refresh, and it probably will work. Yeah. Any other question for the TS? Okay, for this experiment, there are a few parts to this experiment, as you saw. So you have to draw the circuits. Everything is given in the instruction. You just need to follow that. So we will give you a couple of weeks for this. So next week and the week after that, we will have a deadline. Okay, when you have to submit the report related date. So that the instruction that was given, okay, the guidelines, how to write the report, everything is there. Please follow that. Okay, and I'll also request the TS to set up an assignment, okay, with the deadline being 2 weeks later. So next Tuesday, next to next Tuesday. Okay, so you can put a deadline there. Okay, and what else, Professor Somik? You want to add anything else?
Not specifically. I think there is a glitch in that particular differentiator simulation in VLab. So probably if you are not getting the results, please insert the results that you are getting from the VLabs and what should be the correct result. So both of these observations should be there in your report, and that should be fine.
Yeah, exactly. In the guidelines, we have actually given such a thing. I mean, we have asked you to write that, right? What you observed, what is the accuracy? Okay, what you are getting. Okay, so what you observed and what you are supposed to get. Sometimes the observation could be due to some practical reasons, or it could be just because there is a glitch. Okay, so if there is a glitch, please report the glitch. We have no problem with that. Okay.
Sir, I have something.
Yeah. Any Professor Bhattacharya? Yeah. Go ahead, Shubhajyoti. Yeah.
Yes. Sir, like in the previous semesters, for every lab, we had a manual or something that we could refer, like the theory part and those stuff. So, is there any such manual for these basic electronic lab?
There is a manual which is basically suited for the actual, like, the classes that we used to have. Okay, I mean, in physically when you are there. Okay. But for this, the manual is essentially, if you go to the VLab, you have your theories, you have your like how to conduct the experiments, and everything is given over there. So that essentially is the manual, and you have your circuit diagrams also there. So is there anything separate other than this, Professor Bhattacharya?
I think for the experiments in the VLab itself, we have more than enough information at the very beginning of the experiments.
Yes.
Of the theories and all that could be in any standard book, but if you are talking about any lab manual that we used to provide in physical labs, I think the very first page of the VLabs, they provide sufficient amount of information about it. So if you go to like any experiment, before going into the simulation, if you be in the home page, you have certain tab called introduction. So introduction contains all the necessary information about that particular experiment itself. So
yes,
can you please check? I mean, there is a tab called theory, procedure,
Yes,
and simulation phases. Yeah, so there is a theory tab already available in VLab.
Okay, sir, got it.
So for every experiment, there is theory and procedure, everything is given. And even when you're conducting the VLab experiment, in that also you have instructions, okay, how to take the readings. One more thing I will add, that in these experiments, in these 3 experiments, that I mean 3 VLab links, okay, so you have this experiment 4 and 14 and 15, I believe. So in these experiments, you don't need to provide the answers to the quiz. There is a quiz as well. Okay, so quiz was only for experiment 1 because there was no practical, I mean, no simulation experiment that you are doing. So for experiment 2, if you, for your own knowledge, you can go through the quiz, but you don't need to put it in the report. Okay, just the simulation part. Okay, that's what you need to put in the report. Yeah. Any other question, people?
Also, sir, the reports need to be typed, or will handwritten one be also be okay?
Already mentioned in the instruction sheet. It can be
there
written
are
or
as many were telling that no, from the friends, some were telling that no, we were told to give handwritten, others are telling no type. So there
Who
was a
is saying
confusion.
that?
So I don't know, but there was a confusion among friends only. Like when we
It's
asked
written
that-
clearly in the instruction that
please follow the follow the guidelines. I will quote from the guidelines. Okay, the students may quote unquote the students may submit digital report or a scanned copy of a handwritten report with graphs and computer screenshots, quote unquote. Okay, so this is exactly what is written in the guidelines. I don't think there will be anything more clearer than this. So whatever your friends are saying, seniors are saying, keep that in your mind, but don't use it. Okay,
Okay, sir.
follow the guidelines.
Excuse me, sir.
Yes, go ahead.
Sir, like we see that there are 3 separate experiments. So while writing, we will combine and write it about under a single heading, or write the stuff in for the 3 separate experiments.
So you can, this is one experiment. So for every experiment, there are 6 experiments. For every experiment, you submit a report. Okay. So in each report, you can address each and every part of it as sub experiments. Okay. Or part 1, part 2, part 3. Okay. And then you can write. Okay. It's up to you. Okay. So you can either write part 1 and write all the details related to that, or you can have all the details, and under every detail you can put part 1. This is what the say, for example, simulated data. So under simulated data, you can have part 1, part 2, and part 3. I'm going to explain, or you can just have part 1 and give everything under that, and part 2 everything under that, and so on. Okay. So you can always talk about each part as sub experiment or something like that.
Okay.
May I add something, Professor Sen?
Yeah.
So
please.
the thing is that the condition that we have put is that please make one single PDF for the submission, and I mean, you can have like all the theories in one part and the simulations in other part, but it will be more convenient for the TAs probably to check if you make each of these experiments as separate parts. Like part 1, you complete one particular experiment and then go to part 2 and complete the other experiment. It will be easier for the TAs to evaluate, I guess. But whatever you do, try to compile everything within a single PDF and upload it.
Yes, just one file submission. That is very important per experiment.
Okay, sir.
Yeah, anything else? Anything else? Any other questions, students? Okay, so I believe that the private chat boxes have been created by the TAs. You can contact your TAs. Okay, the TAs under whom you are assigned. They will be inviting you to the chat box. If they have not invited, please post. Okay, they will invite. So then you please, if you have any doubt, please post there. Okay, they will clarify. If there is something they cannot clarify, then you can come to us by posting in the particular courses. There is a general post place, right, where you can post. Don't message anything in private chats. Okay, so I am personally not available in private chats in MS Teams, so please don't post in private chat. You might not get any answer. Okay, and anything else, Professor Bhattacharya, you want to add?
No, it's fine. I think, I mean, the message that we want to give you that, I mean, we are accessible and there, but try to interact with the TAs first. If the issue is not resolved, please contact us. So that is the, I mean, steps that we are following. So the TAs should create the chat boxes, and then you should contact the TAs. And if the issue is not resolved, contact us. That's the simple step that we are following. That's all.
Yeah, contact through the course. Okay, within the course you can post, you can chat, but not private chats. That's what I'm saying. Okay, there is a private chat option also in MS Teams. Okay. Anything else? Anybody? So the TAs, Professor Bhattacharya. If there is nothing else, students, if you want to say anything, if there is nothing else from anybody, then we'll conclude actually. Okay, Professor Bhattacharya. So I think we can conclude now.
Yeah.
Okay, so thank you for attending. Okay, and your assignments will be set up, and I also said that the deadline of the previous one will be postponed by a couple of days. That will be done. That will also be done. Okay, in a few hours it will be done. Okay, thank you everyone.
Thank you, sir. Thank you.
Thank you,
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Yes, thank you.
Yes.
Bye bye.